Welcome to our PyData Global tutorial on sktime. The agenda for today would be that we first may have a general introduction to sktime and sklearn. Then we will continue with how we can do forecasting with sktime, and then afterwards we will show different new features from 2022 and 2023. This includes graphical pipelines and improved parallelization, probabilistic forecasting, benchmarking, and also different marketplace deployment and model sharing feature as estimator search, blueprints, serializing, and ML flow integration. So if you're interested in running the notebooks, all notebooks are available in our sktime project. Here is the link to the repository. There are README instruction how to run the notebooks locally, and there's also a link to Binder where you can run the notebooks in the cloud, and then you can just try it out what we are showing you here. So let's start with the introduction to sktime. What is sktime? sktime is a library for time series learning. It's an integrative framework in the time series space, so it implements its own algorithms, but also provides adapters to third-party libraries. The interface is heavily inspired from sklearn, so following the sklearn paradigm, we have a unified interface for object and estimators. In a few minutes, I will show you what that means. We have a modular design. Our estimators are composable and with homogeneous interfaces, and we also support visual informative pretty printing. But sktime is more than just a library. sktime is a welcoming community. So if you like to contribute to open source, we are always happy for a new contributor. Even if you are completely new to open source software, we have a new contributors guide. We have a mentoring program, and you can just join us on Discord. Just drop into our regular meetups or follow us on LinkedIn, or just ask questions in our Discord channel. So what does unified interfaces means in sklearn? sklearn provides a unified interface. I mentioned that sktime is heavily inspired by that. And this means that any estimator basically has 3 steps which have to be executed to make a prediction. First, you need to instantiate your model with the parameters you want to use. Then you can fit the instance of your model to the new data, and then use the fitted instance to predict new data. So here is a nice pictogram with a robot. We have our robot that we are constructing. Then we have our training data. We have a model fitting here, then a fitted model, and then we can do our prediction. So how does this look like in code? Here we are importing a data set from sklearn. We are loading these data set, and then we split these data into train and test set. The xtrain and xtest are the exogenous features, and ytrain and ytest are the data, are the target data. Here we see the xtrain data, and there we have 4 different features. And the iris data set is a flower classification data set. So these are different features of these flowers. And the ytrain is then corresponding to the target of the different flowers. So in the end we want to classify the different flowers using these features. how is the approach in scikit-learn to do this? First, we instantiate the classifier. Here we use a support vector classifier. Then we fit the classifier using the training data and the right train data. And in the end, then we can call predict using the features of our test data set. And then we have here our prediction. Important to note here is that we can use another classifier, and we only have to change the first step. For example, here we replace the support vector classifier with a random forest classifier, and we only have to replace the instantiation of the classifier, and then we can call fit and predict with the same arguments to the classifier, and this will work. And yes, and this is what we are referring to the strategy pattern. Okay. Beside fit and predict, there are also other methods as getParams for figuring out the parameters of the used classifier. For example, here the random forest classifier would have parameters as number of estimators, and these parameters then can be set during initialization. Okay, now let us go on to what sktime is. Sktime basically uses the same approach as sklearn for time series and for different time series tasks, for example, for forecasting, for classification, regression, clustering, annotation, and so on. Some of them are more stable, some of them are more maturing, and some of them are still experimental. In this talk, we mainly will focus on forecasting, since also forecasting is probably the most widely used use case of sktime. So what's the special kind in time series forecasting? In time series forecasting, in the simplest case, we have our time series, our target data y, and then we want to predict the next values of these target data. So that's the temporal forward prediction, basically the forecasting. How can we do this within sktime? It's very similar to sklearn. We load our data, and then we are specifying how many time steps we want to predict. That's the forecasting horizon. But if it's coming to the estimator itself, it's basically the same as for sklearn. We instantiate our forecaster, call fit on it, and then we can predict. And we have here no exogenous features, just the time series itself, which is passed during calling the fit, and then in predict we are specifying here how many steps in advance should be forecasted. And then if we plot this, then we see here that here we have a forecast for the next 36 months in this data set. Classification, time series classification, there it's works similar. In time series classification, you have multiple time series with labels for training, and then you want to classify the unlabeled series. And here we load again our time series. Then we here specify our classifier. In this case, we have a k-numer neighbors time series classifier with some distance, which we would like to use. So here's the instantiation, and then we again just have to call fit using the input time series and right train, and then we can predict. Now here is to note that between the different tasks, between forecasting, between classification, the input differs. In the classification example, we have here 200 instances, one feature per instance, and each instance has 427 time steps. And the class labels are then, we have one label per instance, so we have 200 instances. Okay, so sktime is not only implementing its own algorithm, it integrates a time series modeling ecosystem. The reason is that in the time series ecosystems, there exists a lot of different packages focusing on different kind of algorithms, different tasks, and basically sktime also aims to provide adapters to the different libraries, for example, TS-Fresh, BDM, Arima, Profit, Glue on TS, and so on. And basically, sktime acts in this case as a layer between the different tasks you would like to solve and then the algorithm you would like to use. So what's next? Now, today we want to provide you a short forecasting introduction. This is done by Anirban, and then we will focus on new features that are added last year or this year. So now I will hand over to Anirban, who will present the forecasting.
Thank you, Benedict. I'm audible. Yep. Okay. So let's go on. So hi everyone. So now we are going to see a basic introduction to forecasting component of sktime. We have a lot of other components in sktime focusing on time series classification regression, as Benedict just covered. Obviously, the most popular use case of time series dataset is forecasting, and we thought we should give a basic introduction for the people who are new to sktime. We should start with a very common example that is very popular in a retail use case. For example, here we are going to take a look at sales data. So sktime comes with quite a few inbuilt datasets. One of the datasets is shampoo shells, which is available for 1991 to 1993 monthly sales data. And obviously here our goal is to predict what is going to be the sales count in future months. To handle this problem, we can load the data from sktime datasets, import load shampoo cells, and after that we can just plot with our utility function plot series. We're going to see multiple uses of plot series function through different number of time series, different patterns of data, intervals, originals, etc. We are going to see this throughout this session. So we can just import plot series function, and plot series y is going to create this plot. So as we can see, the x-axis is the timestamp information that is part of this data, which is provided to this through its index, which we are going to see in just few seconds, and the y-axis is obviously the actual values. Now if we take a look at the raw values of this data, we can see this is the format. It is a pandas series with the values being the actual sales for the shampoo sales data, and the index is the time information. So all sktime forecasting, all data type formats that sktime supports for forecasting is going to be very similar to this. What are the changes can happen? If we consider a multivariate dataset as opposed to a univariate dataset like this is, it is going to become from series to a data frame, and but the index will still be a timestamp or something that shows you the information for time horizon. Second, all the observations must always have the time information in index as monotone, so that we have a continuous sequence in time. We do not have say for example suddenly 1991 followed by 1993 and then 1992. That is not going to be allowed. But while you load the data, we have helper function so that you can verify what is wrong, and you can change the m type and sci type accordingly. Third generalization that can happen along this is when you have a panel data or hierarchical data. So for example, in a business use case, you may have data set as say sales for store item level. So in that case, it will be the index is going to be a multi-index. The first values of the index is going to be the hierarchical information, and the last one, and it will always be also for hierarchical, also for panel, the last will always be the time information. So the index type of the last index should be either date time index or just date index, period index, or it can also be range index as long as it is monotone. Now we are going, now that we are clear on what is the expected data formats, we will go ahead with a standard flow. As we covered in the previous notebook as well, that very common step in all ML problems is to split into train and test subsets. We are going to use temporal train test split function. This is a slight modification of scikit-learn's train test split function. Train test split offers you to split the data into train and test randomly. Obviously, you can set the seed, but let's not worry about that. And also, you can do say stratification and etc. But in case of a time series, you should not do a random split because test should always come after train. The time information should be kept into consideration. For that, we have slightly modified the train test split function and have the train test split, and we are going to see at least one more version of temporal train test split when we have exogenous feature later. In this particular use case, what we are saying is take the original data y, split it so that the test size is 6. So it is going to take the last 6 observation of the original data, and that is going to be considered as the test data. It is going to return a tuple, again similar to sklearn, and we are getting y train, y test. If we plot the data using the same utility function as we used last time, and here we see one different use case that instead of a single series, we can pass multiple series and identify what label to use by separate labels in the labels argument. And clearly we can see in the plot, the first part of the data is the training part and the second part is the test part. And we can also take a look at the head of both train and test subsets. Obviously, combining train and test, we should get back the original y completely. Now we have the entire data. Now we need to do the forecasting. How should we proceed? First, let's take a choice of a forecasting model. Let's choose exponential smoothing. We will also take, for simplicity for now, we'll also use the auto ETS model, which is basically the Heineman's modification where it automatically determines what is the best parameter of the model, either trained, seasonality, are they additive or multiplicative. That will choose it now automatically, and we will see at the end how we can do determine it ourselves through hyperparameter tuning. That will be the end of this node. First, when we initialize this instance, this is similar to the structure that we established already as part of the first notebook. First step, we initiate the estimator object. Forecaster is created. Now we pass the training dataset y train that we created just before. We pass that to dot fit call. After dot fit call is over, forecaster state gets changed and it now has the fitted model and all the fitted parameters is there. Now we need to predict. Let's say in this example, we want to predict for next 6 months. So we are specifying 1, 2, 3, 4, 5, 6. So here one thing is to notice that in sktime 0 is always the last point in the training dataset, and so 1 is the next observation in the same unit of time as the original training data. Since the original training data was monthly as inferred from the index automatically, so 1, 2, 3, 4, 5, 6 will mean give us a prediction for next 6 months. If required, you can also specify say 2, 5, 6. It doesn't need to be a continuous sequence. You can vary, and if you want, it can even be like say 4, 1, 6, something like that. If you want, you can give negative values for in sample predictions. Yeah, so once you specify what all you need forecast for, you pass that to the predict method fh equal to fh and get the final predictions. Then you can plot, and we can see here that the orange line is the original test values and the green lines are the predictions that is coming out of the model predictions. So it's very much of a smoothing line which is expected from a exponential smoothing model and doesn't really capture too much of the data sets. We are going to cover different algorithms later, but the main focus of today's session is the use. So we are not going to bother too much about the fluctuation capturing part, but we will still cover some part of it later. Now, since we are see, you can see that it is not capturing fluctuation as a business use case or any use case, we would want to know how we are doing. So we need to create establish a baseline. For that, we need to have a metric. For the purpose of the evaluation, we are going to use the performance metric component of sktime, where we have a bunch of metrics defined for different tasks: classification, regression, forecasting, etc. Obviously, we are in a forecasting use case, so we are going to use the forecasting subcomponent of performance metrics and use SMAP for this occasion. So we are taking map, mean absolute percentage error metric class from the component, and we are going to initiate the metric object with symmetric equal to true. By default, mean absolute percentage error is going to give us map without considering for the symmetricness, so it is going can be infinity and anything. So that's why we are going to switch it to symmetric equal to true, and here this smap we are going to use it throughout. Once we create the smap object, we can just pass the original and predictions and see the errors, and we are seeing it has resulted into 16.7% error. This is our baseline. For that, we should note two things: that we have used smap here, but as I said, we have a bunch of metrics already. If you should use multiple metrics to see what is applicable where. For example, NRMSE, also by Heinemann, is a very good choice in a lot of business cases, much more appropriate than smap, but that's up to your use case. Second thing that we should notice here, we did the train trace split by a single split. We split the entire dataset into just last 6 and everything else. Very often this is not suitable. You should want to do backtesting. So for example, you will split the data into multiple components, strain on some part of it, predict, again update the model, that's what. We will see an example at the end of this term. Okay, so now this is the very basic use case of forecasting. Now we are going to see what all enhancements can be done in different direction. First enhancement we are going to see is exogenous features. Very often, say in a business use case, you know that your variable of interest is something, but you also have other features that affect this variable. In a standard forecasting model that you have covered in say exponential smoothing, it doesn't take those things, but you would want to use those effects, so how they are changing is affecting the prediction of your variable of interest. We're going to see how sktime helps you to consider these cases. For this, we are going to use the Longley dataset. It's a standard dataset from R. The dataset here, the target variable of interest is the number of employed people, and the exogenous features that we are going to use are US macroeconomic features. And based on the dataset, we know that these features are highly correlated. There is too much relation between this, and it is very often used in other statistical purposes as well. We can take a look at how the data looks like. So you can see here y is totem p, and again it's the same format as we see in the previous dataset. The index shows the time information. It's this time it's a period index, and values are the actual number of employed people in this series. If we scroll down below, we can see also the x set and the different features that is coming as part of it. All of them are individual time series as well, but as of now our goal is to forecast y and not any of this thing, not for now. And in all since also this is a past data, so we know the entire data of x for both past and future. But again, it's not going to be the case all the time, especially in real life forecasting problem. You're not going to know what is going to be the x test. How do we use it? We are going to come back to that problem in a bit. So when we have x and we also want to train a model and use this thing, we can use the same temporal train trace split function as we used earlier. This time we are going to pass an additional argument x equal to x, and the output of the function is going to be now a tuple of 4 with the two additional arguments, returns of x train and x test. These will again be in the same type as the input x. So here x was a data frame, so the output is also data frame. So if we scroll down, we will see that again y train and y test goes back to same thing, and x train and x test are combination will be the total x as we had earlier. Now we need to see how to use this feature. Again, continuing the streamline interface that we already had, we are going, the process will be same. We will first create an instance, do a fit, and then we'll do the prediction. So here in this example, I'm going to show two cases. First, when we use exogenous feature, Second, we are not going to use the exogenous feature. Here, some of you from statistic background may have questioned, how does ADIMA support exogenous feature? So here ADIMA is the class name, but it is actually the implementation of SADIMAX, which is coming out of stats model implementation, and we are just exposing it with a uh, consistent interface. So we are going to create two forecaster, both of ADIMA. Both the time we are going to train it with Y-train and try to predict for the next 4 year. But one time we are going to also pass it the exogenous feature. The second time we are going to pass x equal to x train. Now forecaster with x has the additional information with forecaster without x does not have. During the prediction, we are also need to pass now x test to predict with the second model, because for all algorithms, most algorithms is going to need the future values of exogenous feature if they need to use that for prediction. In case you don't know, again, as I said earlier, we'll come back to that problem later half in this notebook. So in this particular case, we have generated two sets of prediction. Once we didn't use x at all, once we used x. And if we now plot the thing, we can see in this graph that the middle line, the more yellowish orange one, that one is the original y test value. The green one is the predictions where we do not use x, and the above line, the deep orange, that is the one where x values are used. From the plot, it definitely looks that using x improves the forecasting performance, but obviously we don't have to judge directly from the plot. We can take benefit of the SMAP object we created earlier. So here we are evaluating the both, and as we can see, the performance improved from 5.9% to 2.8%. So this is an improvement by using X. So here's a small note that not all forecasters in sktime supports exogenous feature. It will give you the same interface. You can still pass X, but it will drop the features because the algorithm is not just capable of handling it. If you want to know which are the estimators that supports it, you can get it using this. So ignorance exogenous X is a specific tag, and what are tags, how do we use it, we are going to cover it as part of the fourth notebook, and Franz is going to talk over that session. So we can now move on to the next section here. Right, so here we are going to do coming to the second enhancements of the quick start that we have. The quick start used a forecasting model where we are predicting y, which was sales data. In the previous also, we are predicting the employed data set. Both times it was a univariate target feature. That's not the case always. So how do we use it when we have uh, multivariate exogenous features? In that case, again, as we have discussed earlier, the dataset is now in the form of a data frame, and the index once again of the period index or any sort of time information. Then we can use few of the forecasts that are purely multivariate, for example, var or varmax. In this particular example, we are using var. Again, similar interface. We're creating the var object and importing var, initiating the var forecaster object, then passing that information to fit, and finally doing the prediction. And the prediction is going to come out like this: our data frame, the similar format that data went in, the output is also in the same format. Two columns corresponding to two different series of the input dataset, and the index is the timestamp information for which the predictions are being made. So in this particular case, one thing to note is that not all forecasters support proper multivariate forecasting. Very few of them are. We can list those by using all estimators. Again, we will cover how this information is stored in the fourth notebook. These are the four algorithm: dynamic factor, var, varmax, vcm to use. How are we capturing? These are the one that can use proper multivariate thing. But what happens if you want to use another algorithm, for example, ARIMA or exponential splitting? But in this, for example, in this example, theta forecaster, you can still use it. The interface is going to be same. What is going to happen in between, because these are not inherently multivariate model, what is happening inside this is we are training two models independently for each column. If you also consider the exogenous feature, that can also happen, But in this particular example, we haven't considered that, but the logic is the same. So in this particular example, when we pass theta forecaster and we pass a y that is multivariate, so it's a data frame. In that case, we are going to create multiple models corresponding to each of the columns of y, and all those columns, all those models is going to be trained independently. This training happens in parallel. And how does the parallelization work? How to improve the performance of parallelization? Those are the things that we are going to cover again in the fourth notebook when we talk about the new parallelization improvements using different backends. Yep. So far we have covered the two main extensions of the quick start. Now we are going to talk about a different feature before we go into the pipeline capabilities. So this is the feature of probabilistic forecasting. So far, all the predictions that we have made, we have used the method .predict. That gives us the predictive mean of the distributions. But a lot of the times that is not enough. We may be interested in confidence intervals. We may be interested in the quantiles of the distribution, something like that. So we are going to use these methods as well: predict quantiles, predict interval, etc. All of these methods are applicable, available for all the forecasters, but not all forecasters support them. We can take a look at below sometime later how to identify which one supports it. But to use, in order to use it, what you need to do is dot predict interval, call that method, and pass a coverage value. So here, what I am asking for is, give me the 95% coverage for the prediction horizon that was already passed during the fitting stage. And it is going to give me in this format. The format is going to be consistent. The column index is going to be a multi-index. First, the different number of features that went in GNP and GNP DFL, then the level of coverage that we asked for, 0.95, within that lower upper. In case you want multiple coverage, for example 90%, 95%, the result is going to be in the same format. We are just going to get more results, and all you have to do is pass the coverage argument as a list. If you are interested in quantiles, it will be the exact same format. In predict quantiles, you will then pass alpha equal to whatever your choice. It can be a single value or multiple values based on your requirements. Now if you scroll down, yeah, so here are the forecasters that have the capability of probabilistic forecasting capability. Predint is a tag that measures it. We are going to cover it later, and we are going to have, there are multiple cases of it, separating the in-sample probabilistic prediction and out-of-sample probabilistic prediction. We are not going to cover details of that as part of this notebook. Instead, we are going to go into the how do we improve our prediction performances through pipelines. As part of this section, we are going to cover three sections. One is how do we use transformation pipelines for Y target variable. We also obviously support for exogenous feature. We are not going to cover that in this section. We are going to cover some part of in the second section in graphical pipeline, which Benedict is going to cover, but we are not going to cover in many details. Second part is parameter estimation. We are going to come into that across this one. And the finally is forecast text. This is going to cover the case where we do not know what is the unknown values of the x that we are going to use for the forecast horizon. Let's start with the first section. Let's consider again another standard data set of air passengers. Again, we load the data and plot the data. So now we will take some time looking at this plot. From this plot, as we can see, there's a clear increasing trend. There is also a clearly repeating pattern. So we can see there's a seasonality, and if you note at the number of points, you will notice that it's a monthly seasonality which is repeating every year. We also notice that as trend increases, uh, the num the amplitude of seasonality is varying. So the amount of fluctuation that is there when the trend was lower, and the amount of fluctuation when the trend is higher is not same. This indicates that the relation between trend and seasonality is multiplicative and it's not additive model. These are all the observations that we can gather from this plot. Now we need to plan how do we focus for this. The idea will be one idea will be we can first take a logarithm of this dataset. So that will directly convert the multiplicative model to additive model. Second, we can remove the seasonality. Then we will have only the trend part left, which from this plot looks like much of a linear plot. Predict the linear trend in future, add back seasonality, and that should add back seasonality, and then we need to do an inverse transformation on the logarithmic transformation. So we need to do exponentiation, and we will get the final forecast back at our original thing. Now we need to see how do we do this. Sktime is going to offer you a very simple step with just a couple of lines code to do this. But let's consider the case what happens you didn't have Sktime. You are going to do in a normal way. We are going to cover this thing first so that you can understand what all things are happening inside, and then we are going to look at the thing how Sktime makes this complicated process much simpler. So first, as I said, we are taking the logarithm of the dataset. So this plot directly shows that the fluctuations in the dataset is no longer variationing as much as it was in the original plot. So here the amount of gap between the high and low in the left side and the amount of gap in the right side is mostly same. So we can understand that from this plot, trend and seasonality are additive now. It's no longer multiplicative. So one step we have progressed one step. Second step, we need to remove seasonality. For that, once again, we are going to take benefit of stress models and we are going to use STL decomposition. Since we have already observed that the seasonality present in this dataset is monthly and it is varying, like changing every year, so periodicity is 12. We are going to specify period equal to 12 during our seasonal decomposition, and by default it already does additive decomposition. We don't need to specify it. If it was a multiplicative, we could have still specified in the seasonal decompose call. Once the decomposition is done, seasonal result object is going to give us the trend, seasonal and residual component. We're going to pick out, extract the seasonal component and remove it from the logged series, and now we are going to plot it. This plot shows now there is no repeating pattern that is present in this graph. So it is mostly trend plus some noise, which is always going to be there. So we done on all the planning that we had immediately planned from the plot. Only thing is left is make the forecast. Since it's a linear model, we are now going to fit a linear forecaster. So we are going to use trend forecaster, which by default use OLS. If we want, we can use any regressor, but we can see it's a linear thing, so that should be enough for us. And we are going to make forecast for the next 1 year. So as we discussed earlier, FH is going to be specified as 1 to 12. You can also do by range. It's the same thing. We support any sort of specification, any sort of sequence specification. We initiate the frequent FH and we pass it to the forecaster object that we just created, and we are getting the prediction. This prediction, however, is not in the original scale of the data. This is after taking logarithm and decentralized, but from the plot, it looks that the predictions are very good corresponding to the transformed dataset. Because as you can see, even for a manual prediction, this looks intuitive. It's not very much. But now we need to remember how do we convert it back to the original scale. So that's the next step. So we go on below. Yep. First, we take the seasonality component that we already created and stored in the seasonal object. We also noted the fluctuation is constant. It's not variating much over the time. So we take 12 components so that January goes to January, February goes to February, and so on, and add that part to the prediction that we just created. Now that we have that thing, we can just directly exponentiate it back and get the final predictions in the original scale of the dataset. And here's the plot, and it looks much intuitive. And if you just assume that the final color was in blue and line, you will probably not even be able to notice that it's not the same graph and it's a prediction. This is how a standard forecasting model, if you didn't have sktime, would work like. How does sktime help us? The help case does is you do not have to remember to all these inverse transformations later. It is going to take care of that for you. For the steps will be, you first initiate the object that you need to create. First, a log transformer. For that we are going to import the log transformer object from the transformations component of sktime. We have a bunch of transformations available in sktime. We're not going to cover all of them and also not focusing much on the transformations component today, but here's just one of them. But we're not restricted to sktime transformers. If you want, you can use scikit-learn preprocessing transformations, you can use a pandas transformation, or even you can even write your own function transformation. We support all of them. Second, we are going to do deseasonalization, which is a wrapper on top of the seasonal decompose function from stats models that we saw earlier. Again, we are specifying sp equal to 12 to say do decomposition with a monthly periodicity considering 12, and by default it is taking the model to be additive. Third, we are initializing the forecaster object. Now, transform target forecaster. This is the main pipeline object which is going to help us. When we initiate that object, we specify the different steps during the forecaster. Take log, remove seasonality, train forecaster. Now, when you train the data and do a fit and then a predict call, what it is going to do is, during fit, it does exactly what we did above. But during predict, it automatically runs the inverse transformations for the two transformers that is part of this pipeline. So in this particular case, when predict is being called, first it is doing the prediction on train forecaster object, then it is inverting the remove seasonality part, so adding back the component. Third, it is adding back the inverse of take flux exponentiation. So if when you are doing the fit predict and plotting the values, as we can see in the below plot, it's identical to the plot that we achieved earlier. Benedict, if you just scroll below. Yep. The plot is the same. So just by doing initiating a list where we maintain the sequential order, we are going to achieve the same performance that we needed to do 7 to 8 cells to do all the functions. There's an even shorter step that is using dunder magic. So for all our forecaster, we have created few dunder functions so that we can do something like this. So take log multiplied by remove seasonality multiplied by trend forecaster. What it is doing is it is doing creating the exact same estimated object as we created earlier. It is saying first take a log on the dataset, then do a seasonality transformation, pass this transformation to the trend forecaster, and the reverse also for the prediction part. This is not the only data magic that we have. We also have similar transformation when we want to do handle exogenous features, when we want to do multiple feature, we can do column select and that sort of thing. We're not going to go into much details of that. If you go to our sktime repository, you can find multiple examples for this, or you can reach out to us in Discord. We will be happy to help you with the links. Now that we have this example, one thing that helped us here is that we could identify that 12 was the seasonal periodicity, that it was varying every 12 weeks, every 12 like after every 12 values, the periodicity seasonality is being reset to the original value. Not all the time you will be able to do that. So for example, you may not be clear, so it may be a quarterly or monthly, and you may not be observing it just from the plot directly. What do you do then? For that, we are going to take benefit of another sktime component, which is parameter estimation. What we will do here is we will go back to our basics. How do we get a seasonality of a series? We make the series stationary first, and then from the ACF I find which are the significant values. That's exactly what we are doing here. First, we are taking a differencer. So by default, it is taking the first differences. In different use cases, you can specify multiple lags. Second, on the difference object, we are going to fit seasonality SCF and find which are the significant lags where it is significant. We are going to do a dot fit y, the original dataset, and the get fitted params method is going to give us the actual fitted values. So as we can see here, SP, seasonal period, short for seasonal periodicity, is 12, and SP significant is 12 and 11. few forecasters that we support, for example, MSTL, BATS, TBATS, they support to handle multiple seasonality for their modeling. In that case, SP significant can be used. For today's session, we are going to be restricting ourselves to the use of just SP. So in this way, you can use to automatically identify what is the seasonality of the data. But this looks like much of a not automated use case, manual use case. When you are doing an interactive model, you are using. How can you use it as part of a pipeline, even for automated process? For a say for a business continuously running a pipeline, the seasonality is changing over time. How do you determine and automatically use it? For that, we are going to use a plugin param forecaster. This is combining the earlier step with the previous pipeline. Here we are going to first create a forecaster object. This time we are going to use one more forecaster object or AutoArima. This is on top built on top of PMDArima's implementation. Then we are using the same parameter estimation object that we created earlier, SPEST, and the forecaster. Plugin param forecaster, SPEST forecaster, what it is telling is first do the parameter estimation on the original dataset, then find the SP parameter, pass it to the forecaster object. How does it know what parameter to pass? In this particular case, AutoArima has the argument that has the name SP, and one of the fitted parameters from the SPEST object is SP. Since it's a match, it's going to learn, infer that automatically and use it. In case it was not automatic, say for example, the AutoArima had a different name, say for example, season periodicity, something like that, we could have used the keyword parameter params and specify that up to our steps. In this way, when we specify and do a fit predict call, continuing our streamline interface, it is actually going to use the 12 that was fitted before. To see that, we can get the forecaster underscore object property of the fitted pipeline object, and as we can see, it's AutoArima with SP equal to 12. 12 was not passed by manually, but it is automatically inferred as part of the fitting and prediction process. And this is a particular example, it's very short of 2 stage. Even if you have, say for example, 30 to 20 transformation steps, first you do a lot of data preprocessing, then you are coming across this page, it will still going to work, and you can combine it in multiple ways. In this particular case, we are lacking some features. So if you want to help us with some more contribution, this is welcome. For example, adding some done magic even for plugin parameters and so on. Okay, so this is closure of the second part of the pipeline flow. So we are going now coming to the third part, that is exogenous predictions. Here we are going to cover the case where we don't know the values of the exogenous features for the prediction horizon. This is actually going to be the most common use case for any business, for example. So say if you want to do a price sales prediction, you may want to use price as your extra feature, but you may not know what is going to be the price in future. It is not always something that you control. It may depend on the several market factors. So for that sort of use case, you don't know price. What do you do? One option, you feed a separate model for price data that you already have, predict in future, and those predictions, you pass those to the original prediction model of sales and use that. That's exactly what we are going to do here. We are again going back to the Longley dataset, load the data, split as we did earlier. Again, we will going to fit the two models that we fitted last time, once with X, once without X. And the second case here, what was the earlier case, forecaster with X, we have renamed it to forecaster with X known. Why? We are going to fit one more model, forecaster with X unknown. In the known case, we are going to pass the known dataset, so xtrain and xtest, in both fit and predict stage. For the unknown case, we are not going to pass the xtest during the prediction, and we are going to see what happens if we try to use the xtrain that was passed before to predict for the future and use those predictions for the prediction of y. That's what we are going to do with the forecast text composite object. It is one second part of our pipeline components. So we are creating a forecast text object. First, we pass an algorithm. which is ARIMA instance in this case, which is going to be used for Y prediction. The second argument, var object, in this particular case, it is different, but if you want, you can also use the same object. If you do not pass anything, that is, you pass none, it will use the same forecaster by default as the Y forecaster. And if you want, you can also pass some other controls. For example, you may choose to train the original dataset. Instead of using the original dataset during fitting, you can also use the prediction value for the forecasted X during the fit stage. This is one of the very new introduction in feature, and that behavior can be controlled using a separate parameter, fit behavior, where you pass use actual or use predictions. Anyway, so once you create the forecast text object, you will fit and predict using the exact same interface that we are doing so far. And let's now see get the predictions and their plots. Right. So we see the three lines that we saw earlier: the deep orange, light orange, yellowish sort of, and the green, and a final pinkish line. That line is the prediction that is coming from the case where we use X only for the training stage, and for the prediction, we are using the already past X to predict for future and to get this. This is the option that you can use for any real life forecasting use case where you don't know X for future. This is covering our forecast X use case. So we are going have come to the last section of the second notebook. Here we are going to see how do we do parameter tuning, and also we are going to see a brief example of backtesting. So what is parameter tuning and when do we use it? So as we started the example, this notebook, we started with auto ETS, and we said we are using the Heinemann implementation of auto ETS so that it can automatically infer whether to use the additive or multiplicative model for the error train, dam train, etc. components. And obviously that's not for auto ETS. Other algorithms also have lots of hyperparameters. You may not always know what hyperparameter to use. In few cases, you may not even know what forecaster to use. You may be choosing between auto ARIMA, auto ETS, theta, maybe something else. How do you decide what to use? We are not going to cover the choice of forecaster in this notebook. That can be done with multiplex forecasters, another capability of sktime. But here we are going to see how do we determine the optimal value of a hyperparameter. This we are going to do with a slight generalization of the grid search and random search already part of sklearn, and we have modified it so add the temporal capabilities. So first we are creating the forecaster object auto ETS, and this time we are specifying auto equal to false, so it doesn't do any automatic inference on its own. But also we are not passing any of the values for error train, dam train, seasonal, etc. ourselves. That we are going to find as part of the tuning process itself. So once we load the data, do a initial split to evaluate later, and we are going to create a forecast object. Now we are going to define the parameter grid. These are all the combinations that is going to be defined, then going to be tested. For example, one particular instance is going to be auto ETS, error equal to add, trend equal to add, dam trend true, seasonal add, SP4. Another instance will be another combination. So in this particular case, so there are 2 4 and 1 3. So 2 times 4, 2 into 2 into 2 into 2 into 3. As many models are going to be tested. If we use grid search, if we use random search, obviously we can take it a bit down. In this particular case, it's a very small data set, so we are using grid search. But in most of the business use cases, you probably don't want grid search. You will probably want to go for random search to improve the performance time. Okay, once you create that parameter grid, we need to find what is best. To do that, we need to create cross-validation splits. For that, we have multiple splitter object, which is once again a first-time object in sktime, and we are going to cover some part of it in the fourth notebook as well. So in this particular case, when we say expanding window splitter, what we are saying is create an initial split which has 12 data points, and the next 6 points use that as an evaluation dataset. Once you are done with that, use the next split where you add it by one more point that is being identified by the step length argument, and evaluate it on the next 6 points. And in this way, you continue. So that's how we are plotting the CV split that was actually created as part of this splitter object. And these are the splits. So as we can see, there are around 12 there are about 12 splits, each with different training data, training part and evaluation part. We're going to do cover all the splits and see what algorithm on all the 48 use cases that we possible instantiation of the model that we see, what works best on an average on all these CV splits. To do that, we need to start with creating our object. Again, we are importing from forecasting grid search CV, and this time we are using the model selection subcomponent of sktime forecasting. Then we pass the original forecaster object that was initiated without any hyperparameters choice. Then we pass the splits that we are going to use. Third, what are the possible options for the parameters? Fourth, how do we choose what option is working better? We initiated a smap object earlier, and smap, since it's directly imported from sktime itself, it knows that smap would mean lower is better. But if you create your own scorer, you are free to do that. You may need to use the make forecasting scorer function as part of the library to make it to specify if better is good or higher is better or lower is better. Finally, we are specifying njob equal to -1 to take into all the processors in the node in the current compute environment. Again, some part of it is going to be covered in the fourth notebook, where we covered about different parallelization backend. Once we initialize the grid search object, we are going to pass the training data, which is ytrain, and we are going to say, okay, train and train for, we are going to target is fit for next 6 points. This final object, when it is trained, can be used directly for prediction. So we can, as you can see here, when we call the dot predict method, we are seeing the predictions for the next 6 months. And if we are curious about what are the best hyperparameters, what are the best codes, we can access the different attributes. For example, best params is going to tell you that this particular choice of hyperparameters led to the best SMAP score across splits as 0.08967. And if you want to see the different values in different splits, that we can also get from CV results attribute and get in this way. So as an introduction to the tuning and forecasting, this is what all we are going to cover in today's session. Now, all the pipelines that we have seen so far are sequential. Like you do something, that argument, the output of that is passed on to only one next step. What very often that's not the case. And to cover those cases, I will hand over to Benedict to cover the graphical pipeline components.
Thank you, Anirban. Now will talk about a very, very new feature, and this feature are the graphical pipelines. As Anirban noted, in the previous notebook, we only considered general sequential pipelines. But what are graphical pipelines? To understand graphical pipelines, let us shortly recap what sequential pipelines are in a more abstract way. So in a sequential pipeline, we have our input, then this is passed to the first step, which might be a pre-processing step, then to the next, which might be an estimation step, and then to the next. Perhaps there's also post-processing, and then we get the prediction. So we have here one data flow, and we execute step by step. However, in general, many tasks are non-sequential. So there might be pre-processing steps that are executed concurrently. We even have multiple concurrent estimators that then are aggregated. So there are many non-sequential workflows. And to solve this, there exists basically two approaches in sktime. The first one is to nest sequential pipelines, and the second one is to use graphical pipelines. And this notebook is focusing on graphical pipeline, on how to use them. In sktime, there is implemented a generalized graphical pipeline. Graphical pipeline here means that the different steps may share the same predecessor. So for example, estimator 1 and estimator 2 are concurrently. They are not dependent on each other, but they got the same input. So they got both input from preprocessing 1. Furthermore, one estimator can also get input from different concurrent predecessors. For example, in that case, estimator 2 would get the input from preprocessing 1 and preprocessing 2. So basically, here we have multiple data flows. The data flows can branch, but they can also merge. And if you are familiar with graph theory, you probably have already seen that this structure here is a directed acyclic graph. And in the following, we will focus on how we can realize complex forecasting use cases with such a graphical pipeline. A side note here is that graphical pipeline is still experimental, so yes, there's a usual risk with such features if you're using them. However, we would be very happy if you try it out and if you provide us feedback on the graphical pipeline so that we can improve this feature. Now let us shortly take a look on the use case we want to focus in this notebook. Basically, we use again the long lay data set. In this case, we would like to forecast the inflation. And for that, we want to use different exogenous features that we require that have to be forecasted. These exogenous features are the gross domestic product, the real DPI, and the unemployment rate. For these different time series, we have different preprocessings and different forecasters, and these different forecaster may use as exogenous features the forecasted data. So this use case we will implement in a few minutes using the graphical pipeline. But first, we have to learn how we can create a graphical pipeline. And basically, there are two approaches for creating them. The first one is to pass all steps during initialization, and the second one is to use an add step method. During initialization, you would create the pipeline object and then pass a list of steps. Important here is that the list of steps, that each step is specified by a dictionary, having at least the keywords sk object, name, and address. Sk object is the sktime, transformer, forecaster, classifier, also you would like to add. Then you have to name the step. You have to name the step explicitly because we can add a transformer forecaster multiple times to the pipeline, and the pipeline itself would keep track of the identity and would reuse then the same instance. And then in the end, we have also here an address parameter which gets dict as a value, and here the x means that the x input of the differencer should be the y input of the pipeline itself. Using the add step is basically the same. So for each step, you would call add step on the pipeline itself. This returns a new pipeline with the added step. And the minimal parameter set would be the sk object, the name, and the address. Besides that, there exists further parameters. The most important one are quarks and method. With method, you can specify the method that should be called on the sk object, here in that case on the differencer. And this is required if we want to control this. For example, if you want to reverse the differentiation after a forecast, you have to specify here method equals inverse transform. In contrast to sequential pipelines, this is not inferable for graphical pipelines. And grarks is a dictionary specifying additional keywords that can be passed to the sktime object. So key messages are here that there are two ways to construct a graphical pipeline, either during initialization or using the add step. In the following, when we implement this more complex example I explained you previously, we will stick with the add step notation. Okay, now let us create this pipeline. First, we create our pipeline object by just calling pipeline without specifying any steps. Now we want to add the deseasonalizer and the scaler. So we add the preprocessing. And we do this by calling the add step method of the pipeline. First, we pass here the standard scaler, and we use here the tabular to series adapter so that the scikit-learn transformer is directly adaptable to time series. We name it scalar, and here we specify the edges. So the X input of the scalar is the unemployment column of the X input of the pipeline. If you have here in the value string 2 underscores, it means that you want to select a column. Here in the deseasonalizer, I mean, that's the second step. There's a deseasonalizer we added. We call the step deseasonalizer. And here, the X input of the deseasonalizer would be the columns. Here we select 2 columns, real GDP and real DPI. Okay, now we have added the deseasonalizer and the scalar. Now let us go on and add the forecaster for the GDP and the DPI. And here we call make reduction so that the sklearn rich regressor is applicable to time series. We name the first one here forecasted GDP. And as edges, we specify that the Y input, which in a forecaster is the time series we want to forecast, is the deseasonalized, the output of the deseasonalized, and more specifically, we want the real GDP column of the deseasonalizer's output. The forecaster for the DPI is also a rich regressor, and here we name it forecaster DPI, and here we specify as the time series that should be forecasted in the time series, the output column real DPI of the deseasonalizer, which is the predecessor in the pipeline. Okay, now we have added the deseasonalizer, the scalar, the forecaster GDP, and the forecaster DPI. Now we want to add the forecaster of the unemployment rate. The forecaster of the unemployment rate depends as exogenous features on the forecaster DPI and the forecaster GDP, and tries to forecast the scaled unemployment rate. So again, we add a rich regressor, provide a name, and now the Y times the Y input of the rich forecaster is the unemployment column of the scalar's output, specified here. As X input, so as exogenous features for the rich regressor, we want to use the output of the forecaster GDP and the forecaster DPI. And here we are using, we are passing these both parameters, we specify here a list, and the list is implicitly using a feature union here. And now we have added a deseasonalizer scalar, these 3 forecasters, and now we only have to add our final forecaster, and we use again a rich regressor, provide forecaster inflation as a name, and here we specify again our input edges. So the X input of the inflation forecaster would be the forecasted DPI and the forecasted unemployment rate, and the time series you would like to forecast is the inflation rate. And now we can just load our data. Here we specify our X and our Y data. We specify our forecasting horizon and then perform our temporal train test split as anyone has shown. Here is our X train data. And now we can just call pipe fit and then pipe predict, and we get our prediction. So basically we have here again the same interface as for all other forecasters or for all other pipelines. Important to note here is that instead of the pipeline itself is generalized. So if you would have added a classifier instead of a forecaster, then it would automatically recognize this, and the predict signature would be of a classifier would be automatically supported. Okay. Now you might ask, how does the graphical pipeline compare to a sequential pipeline? So therefore, let us try to implement a simplified version of the above example, since the above example is not really implementable using just sequential pipelines. And to do this, we have here our figure how the sequential how our final pipeline should look like, and now we have to figure out sequential sub pipelines that we can create. And for example, we can create a transform target forecaster for the GDP using a deseasonalizer as preprocessing. The same for DPI and the unemployment rate. Then we can do a column ensemble forecaster to combine each of these three forecasting pipelines, and then we can use a forecaster X, so that then where the column ensemble forecaster X is forecasting the X value, and then we can specify a forecaster for Y. And this would provide also a forecaster. So here are again these steps, and here is the corresponding code where we are constructing the different forecasting pipelines. I will not dive into it. If you're taking a look into our PyData Prague workshop of this year, then you can see more details on it. And in this pipeline, we can again call fit, we can again call predict, get a prediction. And if we take a look into the get params keys of this nested sequential pipeline, then we see here very long keys. This is caused because we are using so much nesting. And imagine if you would like to tune the alpha hyperparameter of this estimator, then you have to use very long keys for the grid search.
Actually, there is a new feature like that. So if alpha would be unique, you can just write alpha as long as you're using scikit base 0.6.1 or higher.
Ah, nice. I wasn't aware of that. Thank you for this remark, Franz. Okay, so wrapping up, what are the advantages of sequential pipelines and graphical pipelines? Advantages of the sequential pipeline are that sequential pipelines are very easy to use, very easy to build, and very well suited for simpler use cases. They are automatically applying inverse operation in contrast to the graphical pipeline, and they are a major feature, and they are stable. So the graphical pipeline, in contrast, is still in an experimental status. However, the graphical pipeline enables you to implement very complex pipelines without requiring nesting. The parameter structure would be far more easier than of the sequential pipeline in the above example. And you only have to track one estimator compared to the multiple sequential pipelines in the sequential pipeline example. So that was about the graphical pipeline feature, which was recently added. And now Franz will tell you about other new features of the past 2 years in skTime.
Yes, so this is going to be a sequence of very short lightning talks on various topics, 2 big topics: advanced modeling, going to show some parallelism features, parallel broadcasting to hierarchical and multivariate data, probabilistic distributional forecasts, composable time series classification, regressors, benchmarking. And then second batch of features, marketplace and deployment features. We have seen already estimator search in some parts, estimator tags, blueprint, fitted estimator serialization, and ML flow integration. And I fear these 90 minutes are non-negotiables. We'll try to be swift. Now, first feature, parallelism for multivariate and hierarchical broadcasting. We have previously seen already, if you're applying a univariate forecaster to multivariate data, it will automatically broadcast to the columns. So multiple models of the same kind are fitted to the columns. We've seen it in the first part. Now you can parallelize that with any backend that is integrated in the parallelization backend abstraction framework in sktime by using the set config. So every scikit-based estimator object has a config interface, and a set config interface for parallelization of broadcasting. So this is only for broadcasting, is using the backend parallel and backend parallel params keys. In the backend parallel parameter, you can select multiple parallelization backends, consult the set config docstring for it. Loki is droplib's Loki backend, and droplib as the backend parallelization backend of sktime here. Parameters here to parallel are passed via the backend parallel params. We then scroll down, the code remains the same. You need to set the config before you fit and before you predict. And the effect of it is that the code is then distributed to the workers or using the parallelization backend. The same for hierarchical data, which we have not seen, but let me quickly explain. Hierarchical data, that is, if you have in one data set multiple observations across hierarchy levels. So let's say we're observing sales of home appliances in food preparation, food preservation product line and different product group. So total sales by product group, and there could be hundreds and thousands of product groups. So it's a typical parallelization case for your baseline estimators. So let's scroll down. sktime supports hierarchical data. If you have seen that, so pandas with multi-index product line, product groups, the hierarchy levels are the first multi-index levels. If you represent it by data frame, the time is the last level. And you can use the forecasting interface with this kind of data the same way as you would use it with a single time series, and it will predict for a non-hierarchical model. It will apply the forecaster per index per hierarchy level. So let's scroll down a bit because of time. So syntax is very much the same. Fit and predict forecasts are being produced for product groups. Of course, if we have a genuinely hierarchical forecaster, which we will not have time to get into today, then a hierarchical aware forecast is generated. If it's not, then you have the same behavior as in variable broadcasting, same syntax for parallelization via set config. So this applies to both variables and hierarchy levels. Let's move down. So next feature, vignette. Well, this works also for grid search. In estimators, you will have the backend and backend params estimator keys if they're integrated. So it's the same string for parallelization backend, same way to pass parameters. Okay, probabilistic forecasting. We have seen in the first in the forecasting notebook the predict interval method. So this produces interval predictions with a data frame with a column multi-index for coverage and lower upper. There's a few other methods as well. So predict quantiles, predict variance, and predict proba. We have changed how predict proba works in the recent year. Can we scroll down to that, please? The predict proba method now returns a first-class citizen, namely distribution object. So probability distributions of tabular form are now also first-class citizens in sktime. There's also a refactoring effort ongoing with skpro. That's an extension to scikit-learn, where regression estimators can also make probabilistic predictions or interval predictions. Now, these distributions have tags as any first-class object in sktime. So it has potential So distribution type and further information about the distribution. It has its own methods, also a unified interface, scikit-learn-like, such as sample. You can sample from distributions, for instance, if you need it for Monte Carlo business. The distribution that's produced, you can always sample from it. By default, for most estimators, it's a normal distribution. Distributions have a pandas-like interface with index, columns, and log and ilog. So you can use log and ilog to subset the distribution. You can also have access to distribution defining functions like PDF or CDF, PDF if it is defined. And it works seamlessly with probabilistic metrics. So if you want to evaluate a forecaster, for instance, via the continuous rank probability score, you construct it, again, a first-class object, and compare it against the actuals. So note that the second argument here, of course, is not a pandas data frame, but a pandas-like distribution object. All right, moving on. So more about this PyData Amsterdam. Moving on, if you do time series classification or time series regression, you will be aware that your estimators are often highly composite. So many classifiers or regressors, they're based on time series distances, time series alignment algorithms, which in turn are again based on vector distances, so distances on vectors and the real numbers, like normal data sets. One example would be one nearest neighbors using dynamic time warping distance, which in turn use the Mahler-Nobis distance. Now, the change, the re-architecting that has occurred over the last years makes all of these objects first-class citizens based on a scikit base. So all of these objects now have their type and they can be composed and they work with get params. So if you go from bottom to top here, we're building a k-neighbors time series classifier that uses sklearn knn. Then we're transforming an alignment algorithm to a distance. The alignment algorithm comes from the alignment library DTW Python, and internally it uses the distance from SciPy, and the dependencies are of course separated here, and all of these components are individual objects. If you look at the get params or the estimator structure, it works like sklearn. You can now tune or compose all of these objects separately. If you look at the object types, they are transformer panel for time series distances and kernels, aligner for time series aligners, transformer pairwise for vector distances, and of course transformer are the transformers, and you can also combine all of them via Dunder Magic where it makes sense, or you can combine distances to more distances. Many of these distances are compositors. And all estimators here lists all the distances with the type. So there's fewer kernels than distances, but you can also turn kernels and distances or distances to kernels. Alignment algorithms, there are less, but many of these classes, they cover many options in upstream packages. Okay, benchmarking, only going to brush through it very quickly. In the benchmarking module, it's currently very much still a work in progress. Can define benchmarking experiments, adding estimators and adding tasks. For forecasting, for instance, this would be forecasters. The tasks would be backtesting schemas, so cross-validation objects, and data loaders and scorers, adding the task, adding the estimator, then running the experiment, storing the results on the hard drive or in memory is what this module does. Still work in progress, but I think it's a very interesting use case, very interesting area. So contributions here appreciated. The tutorial is also in PyCon Prague. Moving on to marketplace and deployment features. So finding estimators, there's by now hundreds of objects, estimators, metrics, and otherwise of different types. In sktime, so I've introduced a typing system and a system for estimator search, which allows you to list estimators by type and property. To list all forecasters, use all estimators with the forecaster type. We have seen this, but this works for any other type that is supported by sktime. For instance, the splitter type, that's splitter. All types are listed in the registry module, accessible to the registry module. All objects are tagged. So classes have tags and object instances have tags. For instance, the object type tells you of the type. There's a lot of tags that are interesting to the user. Object tags can depend on object parameters, but they will not depend on object state. So here you have tags, for instance, about capability of making in-sample forecasts, and you can produce now tables using these tags. Using all estimator, that might be useful for search. So list all forecasters with whether this forecaster has the capability of in-sample forecast or making probabilistic predictions. You can also use the utility to filter. Of course, you could filter directly via the data frame here, but it's also a convenience function with the all estimators. There's a similar utility called all tags, which allows you to list all available tags with an explanation, what the tag actually means for a given object type. This is very much also a roadmap topic. So we want to also specify scope across packages, possibly second and third party packages, allow also our users to have access to this search functionality across their own packages or across multiple packages in the ecosystem. The estimator overview is also a bit outdated, so we would like to update that. If you're a front-end developer, please make yourself known at the exit. Now, sharing blueprints and models is also possible. If you're, for instance, sharing it inside your deployment system or storing models, fitted models or blueprints, this works similarly but slightly differently. It's also useful for research reproducibility. So let's suppose we want to share the model blueprint for this pipeline. Well, the serialized object is simply the string. Now we need something that reconstructs the object from the string, and that's a method called craft in the registry module. So if you want to serialize a blueprint, simply serialize the string and store the environment with pipfreeze. Then on the receiving end, you can create an environment from the pipfreeze and restore the estimator with the craft utility. There's further supportive utilities. So before you construct the estimator, you can get a more coarse list of dependencies, which is less specific than a pipfreeze. This is the depth utility. It will list the dependencies that are specified by the individual estimator. We specify dependencies on an individual estimator basis. For fitted estimators, for persistence of fitted models, all first-class objects have the save method. This defaults to pickle, but specialized serialization logic can be implemented for things like neural networks. So if you use object.save, it should provide you a serialized object. You can save to a path or you can save to a string. You can save to a path or you can save to memory. If you provide no argument, it produces a serialized in-memory object. From the base module, the load, then it's not a method of a class, but it's a loose method. It also constructs, it also retrieves, deserializes the fitted object, which you then can use for prediction. All right, MLflow, I'm going to skip. This exists. So MLflavor is the package where you can get the MLflow integration from, or of course from sktime also has an MLflow submodule. All right, so wrapping up, thank you very much. We have seen today forecasting, the new updated interface, pipelines introduction, graphical pipeline in advanced modeling with parallelism, probabilistic forecasts, composable time series classification, benchmarking, marketplace features, estimator search, scikit-based interface. And just to reiterate, let's go to the outro. sktime is not just a package ecosystem, it is actually a vibrant community. We are openly governed. We invite you all to contribute, join our Discord, look at our good first issues. There's further material, official sktime tutorial on the main repository. Our vision is to be open source, permissive license, free to use, to remain openly and transparently governed, be friendly, responsive, inclusive. We have a mentoring program. So there's a link to the mentoring program here if you would like to be mentored, to make your first open source contribution, or to be mentored in contributing to sktime specifically. There's a form you can fill out. We have usually four opportunities in the year to start mentoring cohorts. In the summer, we tend to have internships and project opportunities. You can also join our Discord, follow us on LinkedIn for news on events like developer sprints, and of course, star us on GitHub, or better even, donate to help us keep sktime running. Thank you very much for your attention and hope to see you as contributors or on Discord. Say hello, open a good first issue pull request, and looking forward to see you all. Any further questions beyond this, feel free to ask on the Discord help desk channel or in GitHub discussions. I suppose we're out of time now. Hello?
Yes, thank you so much for your presentation. It was fantastic. Yeah, if I think you already posted your slides in Discord, so thank you for doing that. And yeah, we appreciate it.
Thank you all. And thank you, Benedict Anirban. It's always a pleasure to work with you.
Thank you also from my side.
Thank you.
And credits, we should scroll down to the credits for all contributors. sktime is a project which has by now multiple 100 contributors. We use all contributors for contribution assignment. This can also include non-code contribution, such as planning, project management, event management.